Today we're going to look at the normal distribution and apply some more powerful calculation tools now that we have a better understanding of standard deviation and we can see why it's such an important tool. The reason it's such an important tool is because the standard deviation is very closely related and built on this normal distribution, and the normal distribution is so common. We find it all over the place when we started measuring things throughout the world. This is the normal distribution. This is our bell curve. And what this is saying is that if we ever measure a bunch of data, we've learned how to calculate the average. And the average is going to always be right here, right down the middle. We sometimes use x bar, we sometimes use mu. This is the average. So the average is always going to be the line where half of the data is less and half of the data is more. And what statisticians and scientists have found out is that it very, very frequently follows this pattern, with a large portion of the data very close to the average, and then it tapers off into this bell shape with a very low amount of the data being very, very far away from the average. And as they started looking at it, they wanted more and more detail. When they came up with this number, the standard deviation, which was an invented product, very, very frequently, 68% of the data was within one standard deviation, either above or below. 95% of the data was within two standard deviations above or below, and 99.7% of data is almost always within 3 standard deviations of the average. A quick example, let's say we had a test where the average was 60, and the standard deviation, we used the sigma symbol, or SD sometimes as well, was 10. So if we had a test with an average of 60 and the standard deviation of 10, that would mean we'd expect half of students to get more than 60, half less, and then their standard deviations would be 70, 80, and 90, and 100 over here. And then if we step down, 50, 40, 30, and 20. So we had a set of data, we calculated the average, we calculated the standard deviation, and this is what our chart will look like. So when we put the average in the middle, the standard deviations step out in equal increments. So if our standard deviation is 10, 10, 10, 10, or going left, going down, 10, 10, 10. The result is, if we looked at a large amount of people taking this test, we'd expect 68% of all students to score between a 50 and a 70. And 95% of students are going to score between a 40 and an 80. Okay? Just to add some weight to how common this is a chart, or just a little toy that you can buy where there's a bunch of marbles in the top, and as you flip it over, the marbles all randomly bounce off these little pegs, they bounce around, and they fall into the bottom. All the marbles start in the middle, so we'd expect the average to be right in the middle. Half the balls will end up on the left, half the balls will end up on the right, and as we can see, the majority of them end up near the middle, with a very common normal distribution curve being created. We could run this a bunch of times. We see it's not quite perfect, but it's a very good approximation for this sample. And the larger and larger the sample, the more and more balls that we would drop in, the closer and closer we're going to get to this perfect normal distribution. Another example is, this is a chart of the height of 15-year-old boys in Japan. It's sideways, but we can still see here we could calculate the average, which would be somewhere around here. Most boys are about average height, with a few very tall, and a few very short. But again, a pattern that almost perfectly follows our normal distribution. With any measured data, they find that the normal distribution almost always applies, unless sometimes there can be some other explanations for why it does not. But in general, if you were to measure the heights of all the people at St. Joseph's, if you were to take the test scores for the math classes in the province, they would almost always follow this normal distribution. Okay, We can take and break it down a little bit further. If we know the center section is 68%, that would mean 34% in this region and 34% in this region. Okay, we know that 95% are in here, so that would make 13.6% in this region, 13.6%, 2.1, and here we have, if you have a measure of data, if you finished more than 3 standard deviations above the average, that means you are as good as 0.1%. Only 0.1% of things end up more than 3 standard deviations above the average. So let's answer some questions with it to hopefully provide some more details. A light bulb manufacturer claims the lifetime of bulbs is normally distributed with an average 5,000 and a standard deviation of 250. So they make 20,000 bulbs in a day. What percentage of the bulbs will have a lifetime between 4,750 and 5,000? What percentage of the bulbs will be in here? This information is actually, because I borrowed it from the online quiz. We'll start by filling in our chart with our average and our standard deviation. So it's an average of 5,000 hours and a standard deviation of 250. So that means our average is 5,000 and our standard deviation is 250, so we'll step up by increments of 250. So plus 250, plus 250, plus 250. Going left, we're going down, minus 250, minus 2, oh, that's not the right number, minus 250, minus 250. So this is our chart. These are what our standard deviations mean. This is what this number is useful for. And now to answer the question, what percentage of bulbs will have a lifetime between 4,750 and 5,500? So that means we're looking at more than this line and less than this line. So we want to know what percentage of bulbs are falling in this region. What percentage of all the light bulbs they make are going to be in this region? Because they're suggesting it follows a normal distribution, we can see those percentages by looking at these normal distribution graphs. What goes in these two pieces right here? We scroll up, 34.1. We'll use 34.1 and 34.1. So we'd expect 34.1% of the data to be between 4,750 and 5,000, and another 34.1 to be between 5,000 and 5,250. The last piece we need is what goes here. Again, we look at our chart, 13.6. So adding up all three of these numbers is just going to be our answer. 34.1, 34.1, 13.6. Because we need to include all three regions in our chart, and that's 81.8%. So 81.8% of bulbs are going to, 81.8% of bulbs are going to be in our sample space, or going to meet the criteria. Just to take a little bit further, they said they made 20,000 bulbs. So how many bulbs of those 20,000 is it going to be? So if we go 20,000 times by 0.818, 20,000 by 0.818 means 16,360. 16,360 bulbs will, of the 20,000, will be within 4,750 and 5,500 hours. One more example. A university decided that the marks in a first-year English course should be normally distributed with a mean or an average of 65 and a standard deviation of 15. If 2,500 students take the course, how many of them will get more than 95%? Okay, first step, fill out the chart, apply what we know to the normal distribution. So we have an average of, an average of 65 And our standard deviation is 15, so 65 plus 15 is going to be 80. Plus 15 again is 95. Kind of breaks down here. Maybe there's some bonus questions. Going the other way, 65, this is going to be 50, 35, and 20. All right, so these are where the standard deviations would go. Just to quickly talk about it, the school, given this curve, would expect 68% of the students to score between a 50 and an 80. But the question is asking, how many students get more than 95%? How many students are in these two regions? How many students are in these two regions? So if this is 1 standard deviation, 2 standard deviations, this is 3 and up. Back to our charts. More than 3 standard deviations, so this is 1, 2. More than 3 standard deviations is this 2.2%. It's going to be, this is section 1, this is section 2, so this is 3 and 4. We want 2.2% of students. So this whole region together is 2.2%. So of our 2,500 students, we want to multiply it by 2.2%. Careful not to do 0.22. We don't want 22%. We want 2.2. And this comes out to be, what was it, 2,500 times 0.022, 55 students. So the school can expect, given their parameters, 55 of the 2,500 students will score higher than 95% on this test. That provides some connection between the standard deviation we learned to calculate and why it's so important given the common findings of this normal distribution of data.